And yes, welcome back, everyone. I'm so excited that we're here, and I'm very happy that we have Steve Piercey with us kicking things off for 2024. So, since 2009, Steve has been at Memorial University, where he currently holds the rank of University Research Professor. His research, teaching, and consulting interests involve integrated field and laboratory based studies focused on the genesis of mineral deposits and the tectonic evolution of mountain belts, with an emphasis on VMS and orogenic gold deposits. So it's going to be amazing hearing from him today about critical metals in VMS deposits. Thank you so much for joining us today. I really appreciate you having a chat.
Okay, and thank you guys for inviting me and the opportunity. What I'm going to do is I'm going to play this by ear. I have lots of slides, and I'm going to cover a bunch of different things, but I'm going to really talk about VMS deposits, something that I've really focused my career on. But I'm going to give a spin on critical metals, and I'm really going to focus on a few deposits that my students and I have worked on. And I'd like to acknowledge that when you give a talk like this, I've been doing this a long while, and I'm not going to read all these names off, but whenever you work in this business, you get influenced by a lot of your collaborators. And I think it'd be remiss if I didn't acknowledge a lot of the people that have really influenced me and collaborated and supported me in my career. I've worked with a lot of industry participants and a lot of collaborators over the years that have really influenced my work and funded the work, funded the research. Numerous geological surveys, as well as the federal granting agency in Canada. We're really lucky in the sense that they support us for research, but they also support industry-oriented research. So a lot of my research has been partnerships between the federal government and companies, and NSERC has been an important partner for supporting that. And Jess, thank you for the invite. Kathy, for your help, and others for GeoHug staff for getting things out there. And I think it's also important that when you work in a university, a lot of the work that gets done, and you're going to see a lot of it today, gets done by your students. And in Canada, we have a term they call highly qualified personnel when you fill out your paperwork. But I call them the heavy lifting and hardworking HQP, because they're the people that do a lot of the work on a day-to-day basis. And I won't read out the names. You're going to see a lot of these names in talks, but these are all of my students over the last 15 years that have really contributed to a lot of the work that we've done on VMS deposits that you'll see today. Okay, so I'm going to take you on the following journey. I'm just going to start off with just the concept of critical metals or critical minerals in a Canadian and global context. I'll talk about it from a Canadian one because that's where I am, but I'll bring in the US and Australian perspective as well. It's broadly similar. I'll talk about general VMS deposits and how they form, and then the brief challenges to our understanding of critical metals and VMS deposits. What are the main problems in terms of understanding? And then I'm going to just go through a few case studies where I'm going to talk about different metals. So, for example, I'll talk about the main commodity elements that are critical metals in a Canadian context: copper and zinc, important producing commodities. I'll talk about things like tin and indium, which are enriched in some deposits, bismuth and tellurium, to a lesser extent antimony, and then these other ones. And then I'll talk about cobalt and nickel, plus or minus tellurium in another case example. Throughout this whole thing, I'll talk about these things, but also the processes that lead to critical metal enrichments. And what I'll do is I'll end with what I think are things that we need to work on in the next coming years to really improve our knowledge base on critical metals and these kind of deposits. Okay, so critical metals, they're a political term. They're about more or less, when it comes to somewhere like Canada, the United States, they're elements that we need for our economies, for critical technology, and that are also strategic. And so in many cases, they have, restricted supply chains. They're important for national security. And in a Canadian context, we have, as you can see, a nice Canadian maple leaf here. We have just about everything under the sun. But from a VMS perspective, the elements that I'm going to really talk about today are copper, zinc, tin, and indium, and so on and so forth. I talk about the green economy here. A lot of these elements were ones, for example, cobalt. We didn't really look for a lot of that kind of stuff 15 years ago, but now with, for example, electric cars and the electrification of economies, we're looking for a lot of these things for batteries, things like tellurium and so on for medical instrumentation, indium for a lot of our flat screen TVs and visualization. And so when I talk about VMS and critical metals, I'll talk about these minerals or elements and minerals within these deposits. And when we switch gears and look at places like the United States and Australia, a lot of the elements overlap, and in many cases they have the same thing. They're strategic. They have uncertain supply chains in some cases, and we need them for the technology that we need for the green transition and our modern economies. And so I won't go into the details, but a lot of these elements are things that we need. For example, copper, it's the greatest conductor. It is the cloud. It is what runs our electricity systems. Zinc for galvanizing, tin for solder, indium for screens, etc. And so these are the things that we need for running modern economies. Now, VMS deposits themselves are producers of some of these. Copper and zinc are main products of many VMS deposits. The other elements are often byproducts. Some deposits have them as main commodities. But these kind of deposits are similar to what we see on the seafloor, these black smokers. But if you're in Canada, you call them volcanogenic massive sulfides. In Australia, volcanic hosted, and so on and so forth. But what they are, they're lenses and sheets of massive sulfide that form from these seafloor hydrothermal systems where metal-rich fluids, what we call a black smoke, precipitate on the seafloor, what we call exhale on the seafloor, or form near the seafloor where they replace rocks under the seafloor. And I'll show you examples of that. We have exhalative or subseafloor replacement type mineralization. I'm not sure my video is going to work here, but we'll see. Yeah, so this is one of these black smokers that's venting on the seafloor. What these are metal-rich fluids. When these metal-rich fluids come up, they vent. So much of the metal goes up in the water column, and the rest of it actually precipitates in these chimneys, either here or in the shallow subseafloor. Generally, these things form when we extend the crust. So, for example, if we had mid-ocean ridges, arc rifts, back arc basins where we extend the crust and we form extensional faults, and we have upwelling of magmas beneath these extensional zones, or what we call rifts. And as these magmas in place beneath these rifts, we have a couple key ingredients. We have structural preparation of the ground, where faults create permeability to allow fluid to move. And the second thing is we have a temperature gradient. These magmas that are in place have temperatures between 9 to 1200 degrees. Seawater is about 2 to 3 degrees. And what ends up happening, it's like when you put the heat on your stove on a pot. What it will do is that heat differential creates hydrothermal circulation and circulation cells of fluids through the crust. And so what will happen is that the heat differential creates seafloor wanting to move down through the crust and creates sort of hydrothermal, what we call recharge. So seawater itself contains a bunch of different things like chlorine. In the case of the in modern oxygenated oceans and in the Phanerozoic, you'll have sulfate and other various elements. And what happens is as the seawater moves down through the crust due to convection, it heats up, and as it heats up and moves and reacts with the rocks, what will happen is as it goes down, it will actually react with the rocks and strip metals out. Now, there's chlorine in seawater, and when chlorine comes down in this thing and you start to strip out metal from the underlying rocks, what will happen is these metals like zinc and copper and iron, whatever, they'll bond to chlorine, and they'll form metal chloride complexes in solution. And that's important because that's the metals that we're going to use to form these deposits. The second thing that happens is as these fluids move down through, they will actually strip sulfur from the rocks, and you'll get hydrogen sulfide in the fluid as well. And that's the sulfur that we need to form things like pyrite, chalcopyrite, etc. And in some cases, if you have sulfate from seawater, when it comes down, it'll react with rocks and it'll get converted to H2S. And so down at the bottom down here, you'll have a hot fluid. It'll have metals combined with chlorine, so you can transport them in a fluid. They're dissolved in the fluid. They'll have hydrogen sulfide, which is the sulfur that's dissolved in the fluids that needs to form the sulfides. And what will happen then is that if they see certain types of faults, what we call synvolcanic or sedimentary faults, they'll move upwards. And as they move upwards, what will happen is they will vent and form that black smoke. What happens during this venting process is this metal-rich fluid mixes with the seawater, either at the seawater interface or in the subsea floor, and that mixing process shocks the fluid. And what will happen is everything will start to drop out, and the metals and sulfur will combine and start forming these minerals. So this is a general way that these things work. So these are the equations. So you have things that are chloride complexes, things like iron, zinc, lead, etc. These are all in solution. The hydrogen sulfide is in solution. And what will happen is as it comes up, you'll have a fluid, and as it mixes at the seawater interface with, say, 2 degrees seawater or shallow subsurface, what will happen is this will all be destabilized, and these things will start to combine and form the various minerals that we see in these deposits, things like pyrites, sphalerite, galena, etc. And in the case of things like if you have sulfate in the seawater, this SO42 molecule, you can take barium and calcium, and if it mixes, you can also form things like barite and hydrite. These are the things that generally form. So this mixing process is really important. Okay, and what also happens with these things is they actually go through a series of stages. They heat up, they can cool down, and the reason I talk about this, I'm going to talk about the cooling down of a system later. Generally, what will happen is it heats up in stages. This is great work that was done in Japan by folks like Eldridge and Omoto, and also in Australia by Ross Large. Oftentimes, as the fluids heat up, early stages, the fluids are low temperature and they will carry zinc and lead. And what will happen is we'll precipitate things like zinc, lead, and barite. As the fluids heat up, what will happen is once they get above 300 degrees, they can then start to carry copper. And what will happen is that these copper-bearing fluids will come up to the bottom of these mounds. They will dissolve out the pre-existing sphalerite and galena, putting the zinc and lead back into solution and precipitating chalcopyrite in its place. That zinc and lead will move outwards and reprecipitate. And sooner or later, what will happen is you get these well-developed zoned ore bodies with copper at the bottom, zinc, lead, and barium at the edges. And what ends up happening during this process is this goes on and on and on. What happens, you get these well-developed zoned ore bodies with copper and zinc. And the second thing is you get really good increases in grade. And this is just an example of this. This is a photomicrograph of a sphalerite here. And you can see little pieces of chalcopyrite. And this is what we call chalcopyrite disease. And what has happened here is that this is a snapshot of this process. And what you had was a pre-existing sphalerite here. A copper-bearing fluid that was hot came in. It dissolved out the sphalerite that was there, put that zinc and lead in solution, and it disappeared, and in its place, it replaced it by chalcopyrite. And if this goes to completion at the deposit scale, you get something that looks like this with high grades. So this is important for generating grade in these deposits. And we talk about in the modern record, we see these black smokers, but in the ancient record, we also get deposits that form partially under the seafloor and formed by what we call subseafloor replacement. This is just a really good example from the boundary VMS deposit in Newfoundland. And this deposit had venting on the seafloor, but what you can see here is a series of clasts. These fragments here are actually chloride-altered rhyolite fragments, and in between them, you actually see ore. This is chalcopyrite, pyrite, and sphalerite-bearing ore. And what happened in this deposit was you had fragments that were unconsolidated like a jar of marbles, and the fluids moved laterally under the seafloor and filled in between these fragments. And we had what we call replacement. So it replaced sort of the spaces in between the fragments with sulfides. And so this kind of stuff is really common in the ancient record, particularly for big deposits, but many deposits have both, where you have evidence of exhaling and spewing on the seafloor, mixing, and then mixing in the subseafloor, forming replacement deposits. There's been recent work done in the modern seafloor where you see the same thing in the Okinawa Trough just south of Japan, where you have mounds, for example, where you're exhaling on the seafloor, you get zinc, lead rich, and then they move down towards copper rich stuff, these zone refined ore bodies. And then we also have lateral transport, and we replace muds, these pelagic muds and so on. We get these replacement ore bodies where we're replacing unconsolidated muds where you get zinc rich ore bodies that grade into copper. And this is work by Tetsuo Nozaki's group in Japan. And this is him and us last week in my lab here talking about this kind of process here in St. John's. And here's some replacement type core here from Yukon, Canada. Anyways, the point I want to get here is that this process of exhaling on the seafloor is common. Some deposits in the ancient record preserved a replacement. Most probably had both. And we often see this well-developed zoning pattern and so on, where we get copper and zinc in these systems. Okay. There's also subsets of systems, both in the modern and ancient, particularly a lot of work in the last couple of decades in the Pacific, where we look at these hydrothermal systems on the seafloor. Not only do we get this sort of seafloor hydrothermal circulation where there's leaching, but there's also evidence for the magmas that underlie giving off fluids and metals to the hydrothermal systems. And this is just some examples from the Kermadec Arc north of New Zealand, and near White Island. And what these are venting, they're actually venting vapors that contain gases and everything that from underlying magmas that emanated, for example, fumarolic emanations of metals and so on and so forth. So some deposits in the ancient record will have evidence for that hydrothermal circulation, but also evidence for these magmatic, like these intrusions at depth, giving off fluids. And in these fluids, they contain metals. And this is really important for many critical metal hosted deposits. And I'll give a few examples here today, but a lot of deposits that have gold enrichment, silver enrichment, antimony, tin, bismuth, and tellurium. Many of these critical metal enriched deposits actually have evidence for both leaching and hydrothermal circulation, and then also venting from magmatic fluids. All right, so the other thing that happens in the ancient record is that many of these deposits, when they form in specific tectonic environments. I talked about these rifting environments, so things like mid-ocean ridges or continental rifts. But in the ancient record, most of the deposits that are preserved formed in what we would call arc zones, where they rift in back arcs, rift in the arc, or rift in fore arcs, and so on and so forth. And what happens is these extensional environments in the upper plate, when we accrete them back into the continent, these basins that were extending at the time, they actually get inverted and form what we call thrust panel belts and so on, and thrust belts. And what often happens is that many of these VMS deposits, while forming in these kind of environments, end up looking like this later on. They get overprinted by structure and deformation. And this is from Portugal. This is from the Neves Corvo ore bodies. And all I want you to get from this is that this was once an extended basin that was under extension. And now what we have is a series of thrust faults, and this deposit has been disrupted. And this process of deformation and metamorphism can actually influence the ore bodies and actually remobilize metals, and in some cases upgrade them to increase grade for some of these different metals. And I'm going to give a couple examples of this later on where we can see this process happening. And it's a really great paper. This is one written by one of my mentors, Joanne Nelson, from 1997, and it's called The Quiet Counter-Revolution. And it's all about how do we take these basins that once were extending and then look at them later on, and we can see these sort of thrust panels later on. And this deformation process is really important in many cases for remobilizing metals and increasing things. So, okay, so let's leave with the summary so far. So these VMS deposits are generally forming in these extensional settings. You have magmatic heat that drives hydrothermal circulation. As these fluids move down through the crust, they leach metals from the substrate. So the underlying rocks will get leached by the hydrothermal fluid. And that is one of the main sources of metals. And in some deposits, what happens is we get these intrusions that emanate magmatic hydrothermal fluids and add metals from magmatic hydrothermal fluids. These two things are going to be important throughout the talk. Sulfur, I'm not going to talk much about this from here on out, but generally derived from leaching of those rocks as the fluids go down through. And seawater sulfate, in some cases you get it from bacteria or magmatic fluids. They can exhale on the seafloor, replace beneath the seafloor, and many of these districts, they start off as extensional environments, but when you accrete them onto continents, you get what they call basin inversion, and you get these fold and thrust belts. And this process often leads to structure and metamorphic overprints, remobilization of metals, and this can be important in some of these deposits in terms of upgrading grade, but also for moving certain types of critical metals around during the deformation process. And I'm going to give examples of most of these things in the next few slides. I'm going to show this, and the main reason is that if you're a Canadian, many of these deposits are obvious, but I want to put this in context. I'm going to talk about a bunch of different deposits in Canada as examples, and then a couple deposits in Europe. I'm going to talk a lot about stuff in the Newfoundland and New Brunswick Appalachians. I live right here. I'm going to talk about some deposits in central Newfoundland. You'll hear about this Ming deposit, Little Deer and Whales back, and then some, there's going to be one picture from this one here called Tilt Cove. I'll also talk about this deposit here in New Brunswick called Brunswick number 12. This is one of the biggest VMS deposits ever and the biggest zinc-rich VMS deposit on the planet. I'm going to talk about that one. I'm going to talk about Kidd Creek. This is an Archean deposit in Ontario. It's in the Abitibi Greenstone Belt. And then two deposits here in Yukon, one called Fire Lake or Kona, and one called ABM, and these are in the Canadian Cordillera. The other two deposits I'm going to talk about are ones in Cyprus in Europe, as well as the Neves Corvo deposit in Portugal. Okay, so this is just to put it in context so I don't have to come back to this map over and over. So when you hear about these things, I'll bring it in, but I just want to give you an idea where it is in space. Okay, so when it comes to understanding critical metals and VMS deposits, there's a lot of challenges. Number one, many of the deposits have vintage data, many of which do not have any analysis of many critical metals. So they'll have the ore elements that were mined, but they won't have anything else. Even with deposits that have many deposits, many of the assay methods that we use, for example, 4-acid or aqua regia, they don't dissolve some elements. So for example, if you have cassiterite in your samples and you use a 4-acid digestion, your tin values are probably underreported. So in many cases, a lot of the critical metal values that we have and have been analyzed are not that great. We don't have good control on them. We don't have a lot of it. We don't have necessarily good control. And then the second thing is that it's often challenging to find reference materials and standards for doing critical metal analysis in ores. And this is getting better, but just simple things like how good is the data, what are the errors, quality control, and so on is a challenge. And I think one of the bigger challenges is that most VMS deposits have resource data for commodities of interest. And what I mean by that are the ones that get mined. However, the byproduct elements that are often the critical metals, things like cobalt, bismuth, tellurium, tin, indium, etc., we don't have resource data. So you have sometimes data reported to say, yeah, there's an indium zone or a tin zone, but we don't really have ideas of grades and tonnage and the amounts of materials in these deposits. So within what I would call a 43101 or JORC resource context. So oftentimes there's a lot of uncertainty in terms of how much exists in different deposits. I think another big thing is that a lot of deposits, we don't really know where they sit. The residence of the critical elements, and what I mean is where do they sit in terms of what minerals, and in what abundance, is not well done. Most VMS lack sufficiently detailed ore mineralogy with exceptions, and this is improving, but a lot of work that was done on VMS deposits, particularly ore mineralogy, was done like 20, 30 years ago, 40, 50 years ago, before we had really high resolution microprobes and lasers. And so a lot of the data we have, we don't really have a good understanding of the metal resonance and these kind of things. And I think that these are things that I'll come back to later. But I'm going to give you some examples where we do have a better information. And this is a good table. This is from 2014. It just gives you an idea of the general concentration of trace elements and critical metals and VMS deposits. These are not all critical metals, but it gives you an idea of how much is there. Things like arsenic, antimony, cadmium, up to 1%, et cetera, et cetera. What really strikes me about this is that there's a paper written a couple of years ago on seafloor massive sulfides on minor elements. And we have a better understanding of concentrations of these kind of elements on modern seafloor systems than we do on land. And part of the reason is that, number one, the things that I mentioned previously. Second of all, this data exists in many cases, but it's in company databases that are not publicly available. So a lot of people don't get access to this kind of information. And so there's a big effort going on now, at least in the massive sulfide world, to get basic baseline concentration data on ores to figure out the abundance of these different critical metals and VMS type environments. But just for reference, this is a good thing to have in terms of understanding relative concentrations of different elements. And I'll give you some examples of the different concentrations as we go through when we can find it. Okay, so I'm going to look at different groups of elements in VMS, look at their resonance and then genesis and why we have them. I'm going to talk quickly about copper and zinc because these are the most important commodity elements that get produced by VMS: tin, indium, bismuth, thorium, with a lesser extent, antimony and tin. And then I put these in because they're often associated, but whenever you see red in the next few slides, they're not critical elements, but they're often associated with the critical elements. And then I'll end with cobalt, nickel, tellurium, and antimony as examples. Okay. So look at copper and zinc. These are just plots. This is work from Alan Galley. This is tonnage and then grades in terms of average grades of VMS deposits globally. You don't need to worry about the details here. When I talk about copper, I'm going to start with this, and then I'll talk about zinc. But if you look at the copper, they're associated. There's a bunch of different subtypes of VMS deposits. And the ones that have green generally have associations with mafic rocks. The ones that are more yellow have associations with felsic rocks or continental crust. And one of the things that you see right away is that the mafic dominated deposits generally have higher copper grades. And one of the arguments that's made is that the reason for this is that the host rocks that host it and that the fluids go through are mafic, and mafic rocks generally have more copper. Therefore, the deposits that are hosted in these rocks should have more copper. This is not rocket science, right? You know? In contrast, when we look at the felsic rocks, many of the felsic rocks themselves, they generally have higher zinc concentrations. And part of the reason for that is that many of the felsic hosted deposits are associated with continental crust, and continental crust typically has higher zinc concentrations than oceanic crust, and so on and so forth. So what ends up happening is we end up getting zinc enrichments in areas underlain by continental crust and more copper enrichments in areas underlain by mafic crust. There's some really interesting work done by a number of authors, but this is just a recent study done by Simon Jowett about 10 years ago. And what he did was he looked at Cyprus, which is one of these mafic dominated systems. And one of the things that has been argued is that there's a distinctive rock types, these what we call epidocites. And they often look like this. We have these basaltic sequences or mafic dikes, and we have these patches of epidote. And what he did was he studied these patches and compared fresh rocks relative to the epidote patches. And what you notice in it is that in these epidote patches, you have depletions relative to the host rock in the metals that are found in the deposits themselves, things like copper, zinc, etc. And so one of the arguments that's made from his work and some other workers is that as the fluids went down through mafic rocks, they altered the rocks and they leached out the copper. And so the copper itself is coming from the underlying rocks that underlie these districts as the fluids move through them. So mafic rocks have lots of zinc and copper, you get more copper and zinc from leaching of these rocks. And this is a bit of a complex slide. The only thing I want you to get is that zinc and biotite, zinc and muscovite. This is work from Australia by a guy named Hammerly. And what he showed is that if you look at biotite and muscovite, as you interact a fluid with it, as you increase temperature, what happens is the concentration of zinc and biotite and muscovite goes down. And his argument is that this is due to leaching from the hydrothermal fluid. And if we look at a VMS deposit, as the fluids move down through the crust, it's more or less akin to going up metamorphic grade, increasing in temperature, increasing and so on and so forth. And the idea is that zinc is hosted in things like muscovite and biotite and things like the continental crust. And as we run a fluid through it, we can actually get that zinc out and put it into our VMS deposits. So when you have continental crust, there's lots of muscovite, biotite. Felsic rocks have lots of muscovite and biotite in basement rocks, and as these fluids leach, they get the zinc from these kind of things. So key thing for copper and zinc, generally we leach these things from footwall rocks. If you have mafic and ultramafic rocks that dominate the footwall, oftentimes you get copper-enriched deposits from leaching of the metals from footwall. If you have continental substrates with lots of biotite and muscovite, you often get zinc-enriched deposits. There are some big deposits like Kidd Creek and Brunswick 12, which I mentioned earlier. Many of these have really, really high tonnages of copper and zinc. And some people have argued that not only do you get copper and zinc from leaching, but you may have magmatic fluids. And there's other indicators on that. And I'll talk about that later on when we talk about tin and indium. Key point for these main things, copper and zinc, the composition of the footwall rocks matters. And you get copper in more mafic dominated things, zinc in more continental dominated environments. Okay. So let's switch gears and look at tin and indium. So these are often byproducts in VMS. There's a couple of deposits where they're main commodities, but generally they're not the main commodity of interest. These kind of deposits, tin and indium, they're often in what we call, for example, tin-silver districts, these magmatic-hydrothermal systems like we would see in Bolivia. But there's a few VMS deposits that have high tin and indium grades. One that I mentioned earlier, Kidd Creek, Neves Corvo in Spain, and another one is Brunswick 12. And what you'll notice, however, is unlike copper and zinc, which are often at multi-percent levels, these are at like, 1,000 to a couple of thousand parts per million tin. And in the case of indium, these are in tens of parts per million. So relatively low concentrations, and they're often byproducts, not the main source of materials, with rare exceptions. I'm going to just show you a plot of indium versus tonnage of deposits. Part of why they become important in the place of Kidd, Brunswick, and Neves Corvo is that these are really big deposits. This is indium grade versus tonnage. 1 and 2 here. These are Kidd Creek and Brunswick number 12, and number 4 here, this is Neves Corvo. And so even though things like indium and tin are only in tens to hundreds of parts per million, these deposits are really, really big. And correspondingly, there's lots of these elements in it, and you can get it out as a byproduct, and they often get it as a credit at the smelter because of the concentrations and so on and so forth. Okay, a really good example where tin is a main product in a VMS environment are the Neves Corvo ore bodies in Portugal. It's in the Iberian Pyrite Belt located down here. And this is an interesting deposit in that it has many types of alteration, things like chlorite and sericite and so on, which is really typical of VMS deposits. And you have metals like copper, zinc, etc., like in a VMS, but it has really, really high tin in certain areas. So you have these things, what we call massive cassiterite zones, and what we call a tin corridor. And so they actually produce tin from certain lodes in this as a primary commodity. And just to give you an idea, this is just a map, the Corvo ore body through here. The tin ores are shown in gray. They're spatially associated with copper ores. There's a cross section roughly through here. And the only thing I want you to get from this is there's this common association of tin, cassiterite ores shown through here. And they're spatially associated with what we call these rubane ores and copper ores. So this is copper-rich ore. This stuff here is rubane ore. And so we often get this tin association with copper. And these things also have indium associated with them. So you'll have chalcopyrite, cassiterite, and indium-bearing minerals and so on in with them. And just to give you an idea of grade, there's another map coming up. And what this is an isopac map that shows the grades of tin. Some of these are rather exceptional. So this is an isopac map through here. And you look through here, some of these zones are up to 30% tin. So this was one where this ore body was actually mined as a tin ore body. So quite an impressive ore body. And the ores look like this. This is massive cassiterite. Locally within this, you'll have actually roquasite, which is a copper indium sulfide, and so on and so forth. And one of the arguments for this deposit is that it's quite complex. We have these sort of extensional environments. There's lots of stuff going on in this diagram, but the only thing you really need to get is that they argue that some metals, for example, are forming as a result of leaching. So we have hydrothermal fluids that go through the crust and leach out things like iron and zinc and lead, and they're driven by magmatic heat. However, we have tin, for example, tin, some of the copper, indium, and possibly gold is coming from magmatic fluids that are coming off intrusions at depth. So you have these hybrid VMS where you have heat driving hydrothermal circulation and then magmatic fluids adding metals as well. So you have sort of this magmatic hydrothermal component to form in some of the critical metal enrichment in this deposit. Another one that had production of indium and has elevated tin is Kidd Creek, which is a deposit in Ontario. I'm going to get you to look at this. This is the 2,300-foot level of the north ore body of the Kidd Creek mine. This is one of the biggest mines in Canada, still producing at 6,000 meters plus, or 6,000 feet plus, sorry. It's a really well-developed ore body. This is a plan map. You can see zinc-rich zones that has well-developed zoning from zinc-rich to copper-rich and an underlying copper stringer zone. And this deposit actually produced indium as a concentrate. It had a concentration of 270 ppm indium, and it produced about 50 tons of production per year up to 2010. So it was a commodity that they produced significantly, and it was one of the bigger indium producers in Canada. What I'm going to do in the next slide is I'm just going to show you some metal zoning patterns to show you the tin relationships to sphalerite and zinc-rich mineralization versus copper. And so what will happen is this panel right here will be the next panel. So remember, it is zinc-rich, chalcopyrite-rich, and then a stringer beneath. And this is the distribution of metals within that zoning. And so this is zinc distribution. So and copper. So copper at the bottom, really high-grade copper, stringer systems, and so on. It's overlain by high-grade zinc and then lower-grade zinc and classic VMS zoning. But if you look at things like tin, there seems to be associations with both zinc as well as with copper in this deposit. So you have zinc, tin associated with both zinc and copper. And so it's interesting in this one is that there's actually a difference in mineralogy of the tin minerals depending on the association. So these sphalerite-rich ores that have zinc typically have an association with cassiterite, so tin oxide. In contrast, the copper-rich ores generally have stannite, which is a copper sulfide. And they also have this mineral here called roquasite, which is an indium-bearing mineral. So the indium and tin in this ore body, when we see indium and tin together, they're almost exclusively with chalcopyrite and copper-rich fluids. In contrast, the tin associated with sphalerite is always cassiterite. One of the arguments that's been made is that you can get tin both at low temperature and high temperature, whereas indium only occurs when you have high temperature fluids and potentially associated with magmatic fluids. I'm going to just jump. This is an interesting one from tin relationships with tonnage for the Brunswick district in New Brunswick. And this is work that was done by Dan Boyle, but Wayne Goodfellow and Steve McCutcheon. And one of the things they showed is that the bigger the deposit, the higher the tin grades for the most part in this district. And they argued that the tin mineralization that we see in these deposits is coming from magmatic fluids. Moreover, the size of these deposits is actually coming from magmatic fluid interactions. And just like you see in a place like Nevis Corvo, they argued that some minerals and some elements, for example, zinc, lead, copper, and everything can be formed by leaching. And that adds so many elements. But the things that are critical metals like tin and indium and antimony, they're actually coming from magmatic hydrothermal fluids. And so there's this story with many of these critical metal enriched ore bodies where we have both leaching and then magmatic fluid interactions. Okay. So tin indium districts, it seems that we have associations with black shales and what we call bimodal volcanic activity. You have both low, high, and temperature associations, so zinc-rich with sulfides, copper-rich as well. Some evidence that the copper, indium, tin associations have a potential magmatic fluid influence. And in many of these districts that just have tin, sometimes you have black shales, and that might be important, but I didn't really go into that too much. Okay, so that's those guys. All right. I'm going to give a couple more of the bismuth tellurium examples, and then I'll go into cobalt and so on. And for this one, I'm going to talk about, this is what we call the Ming ore body in central Newfoundland. It's hosted in an ophiolite sequence. However, when the ophiolite rifted, you get these rhyolites. This is what we call the Rambler rhyolite, and this hosts the Ming ore body. And the Ming ore body has a bunch of different zones, and I'm going to show a sort of a cross section of these different zones of mineralization in the next slide. And they have abundant bismuth and tellurium, as well as things like antimony and tin. And these things are all associated with things like gold and silver as well. So it's quite an interesting ore body. And this is work from one of my former PhD students, Steph Bruckner, who I'm going to talk about more of her stuff. The deposit itself has a whole bunch of different zones, and the different zones are have different minerals and so on. There's this one on the bottom here. This is what we call a footwall zone. And this footwall is dominated by chalcopyrite and pyrrhotite, mostly copper dominated. There's not a lot of critical elements besides copper in this. In contrast, you have these different other zones, the 1806, 1807, etc. These are sulfide zones. And these things have variable enrichments in things like bismuth, tellurium, tin, gold, and silver. And a lot of work that was done by my former student, what she showed was that, again, this is another example where we have typical VMS type activity, but also magmatic fluids and then subsequent metamorphism. And so just to show you some, these are photomicrographs of some of the ores. So you see typical VMS related minerals, things like chalcopyrite, pyrite, sphalerite, galena. But we also see weirdos that are not commonly associated with the garden variety VMS. Things like electrum, this is gold, gold and silver. Oftentimes this has abundant mercury in it, which is kind of strange for a VMS deposit. Has arsenopyrite, stannite. You get these silver sulfosalts, so things like silver with antimony and arsenic, tetrahedrite tennantite. So the enrichment of what we would call epithermal elements are really common in here with this VMS deposit. We also see like a whole suite of really, really interesting minerals. She documented, it's a really great paper in Ore Geology Reviews where she documents a lot of these really strange telluride minerals, antimonides. You get things like claustolite, these selenide minerals, ones that we don't often see in VMS deposits, but they're always present here in these deposits when you see things like gold and so on and so forth, and silver. And so her argument here is that a lot of these things are actually have a VMS system, and a lot of the things like the tellurides, the selenium, antimony, etc., are all coming in associated with magmatic fluids. And the deposit itself subsequently gets deformed. And you get some really cool textures like this, where you see these intergrowths. This is altaite, which is this is a lead telluride, hessite here. This is a silver telluride. You get bismuth tellurides, and this weird kind of almost like a zebra skin thing is actually interpreted to be due to actually deformation and a remobilization and reorientation of these different elements into these different mineral phases. Likewise, in this one, these are actually pyrites that are deformed. And what you can see along the cracks in the pyrite, you'll actually see alloys of gold and silver and so on. So this stuff was probably there to begin with that formed during VMS activity, but it's been subsequently remobilized and upgraded during metamorphism. And her argument for this deposit is that you had a VMS system that started off life at high temperatures, and you formed a whole bunch of VMS minerals like copper, chalcopyrite, pyrrhotite, etc. These things probably formed from leaching. As it cooled down, you started to form sphalerite, arsenopyrite, and so on. And then at the later stages of the formation of the deposit, you started to get a magmatic fluid, and you get things like tellurium and bismuth and gold and silver and so on. The idea is that you had a VMS system that was circulating, leaching, and then there was these magmatic fluids that dumped in these bismuth tellurides and selenium, gold, and silver as magmatic fluid input. So again, the same kind of story we've seen elsewhere is that you have VMS for some minerals that are leaching, and then some of these late magmatic hydrothermals that are bringing in some of the critical elements. Okay. And then as this thing gets, this formed in the Cambrian and the Silurian, it gets deformed. And when it gets deformed, you start to see this redistribution and remobilization of some of the tellurides and these interesting textures that you might not have been able to get, and you might not have been able to form if not for the subsequent metamorphism. Okay. We see similar things in the Yukon, where one of my students has found these things. This is just an SEM image of some ore from the ABM deposit in the Yukon, and these are just element maps of different elements. And the only thing I want you to get is you get this weird texture here where you get galena and then all these other weirdo minerals in here that are sort of forming what we call symplectites. And one of her arguments, and it's very similar to the stuff that Steph Bruckner showed, is that a lot of these critical elements like antimony, selenium, bismuth, and whatever, they have really low melting points. And this may be an example of what we call sulfide partial melting, where during metamorphism, these things remobilize and you actually get partial melts and you form things that are critical metal enriched partial melts. And this is some of the work that Andy Tompkins did a long time ago, but we're seeing on a nanoscale here in some of these deposits. So some of these critical elements, they were probably there to begin with, and during metamorphism, we just helped to concentrate them along later by a different process. So I'll leave you with that with these guys. Enrichments in bismuth and tellurium and other epithermal sweet elements in these things, including gold and silver, they're likely influenced by magmatic hydrothermal fluids. And one of the things that's interesting is metamorphism and deformation can result in sort of what we call mineral breakdown and these myrmekitic intergrowths of the various critical mineral phases. And this metamorphic process seems to allow this sort of liberation and moving things around so that we can actually get some of these critical metal rich minerals forming as during secondary processes. And in a few weeks from now, you'll see Taryn Kaywood's talk where she focuses a lot on this. And this is a lot of the focus of Steph Bruckner and others' work on this area. Okay. All right. So the last stuff I'm going to talk about is really about cobalt, nickel, as well as a couple of other things, tellurium, antimony, selenides. Cobalt and nickel and VMS deposits, some deposits actually produced it. So it's very common in what we would call Bechy type deposits. So for example, some of the deposits in Japan produced cobalt, and some ophiolite hosted deposits as well. Those that are dominated by mafic and ultramafic rocks plus or minus sedimentary materials often have this. There's examples from Bechy, Windy Crag in British Columbia, and I'm going to show you an example from Fire Lake in the Yukon. Many of these deposits often have cobalt in the resource, and I'll show you an example. This one actually has cobalt calculated as part of the resource. And some of them also have other things, these nickel, arsenic, antimony, and tellurium bearing phases, often as small grains. And I'll give you a few examples. And similarly, this sort of metamorphic upgrading seems to be important in some of these deposits. Often these cobalt, nickel enriched zones are associated with high copper zones in the VMS deposits. So you have a copper, cobalt, nickel association, often with pyrite, chalcopyrite, and pyrrhotite. And these tellurides and arsenide minerals are often in deformed grains and potentially related to metamorphic remobilization later. Okay, so I'm going to talk about a deposit quickly in here. This is just to give you an idea. This is Alaska, Yukon, British Columbia. Just to give you an idea, we're Canada. This is where we're sitting. This is the town of Whitehorse in Yukon, and I'm going to talk about something in right through here. And this is one that's called the Fire Lake deposit. And this is just a cross section through the deposit. The deposit itself comes in a bunch of different zones. The footwall itself is hosted by volcanic rocks, mafic volcanics that have a specific composition. They're called bonanites. They're often cobalt and nickel rich rocks. These things are overlain by a sequence of what we would call mixed metasedimentary metavolcanic rocks and then metasedimentary rocks. These things are more or less turbidites. So you have these mafic rocks that are enriched in cobalt and they're overlain by turbidites. And they have these sort of linear zones, and this is what the ores look like. So you get these really chalcopyrite, pyrrhotite, and pyrite-rich ores, and locally they're cut by magnetite. This is the stuff that these kind of things would actually have copper, minor amounts of zinc, as well as cobalt. And this is just to give you an idea of the resource, 12.5 million tons. This is the copper grades, and this is the cobalt grades from the deposit as well. So you're about 0.1% cobalt in the deposit, and this is generally pretty good grades, relatively speaking. Okay, relative, the ores themselves are actually quite simple, and they're often associated with pyrite, chalcopyrite, and pyrrhotite, locally a bit of sphalerite. And so I had an undergrad student work on this a few years ago, Kyra Kennedy, and she did a bunch of microprobe work to try and understand where the cobalt is resident in these various mineral phases. And it turns out that the vast majority of cobalt actually resides in the pyrrhotite. And it's just to give you an idea, these are sulfide stringers, chalcopyrite stringers in host rocks and massive magnetite. For the most part, when you have chalcopyrite pyrrhotite together, you get cobalt enrichments. And this is just an idea of how much cobalt is in the pyrite, 0.6, 0.35, and the massive sulfides themselves generally don't have too much cobalt whatsoever. And so most of the cobalt's associated with pyrrhotite in this deposit. And I'm going to show you, we went and did some calculations to figure out where the cobalt might have came from. And this is the deposit here. This is an old map from my colleague and I, Don Murphy, and I mentioned that it's associated with this DMF unit here. This is a unit that has really, really high cobalt and nickel concentrations that has what we call bononitic compositions. And these things are spatially associated with ultramafic rocks. I'm going to show you a cross section through here. And so when you see this deposit, the deposit is sitting right here. And then this is just a general cross section. The footwall rocks, these are these bononites through here. These are these ultramafic rocks. And both of these units are really, really enriched in cobalt. And so the assumption has been made is that the cobalt itself is probably coming from fluids that leach cobalt out of these different volcanic rocks, brought them up, formed the deposit. And so in order to test this, my student, Kyra, did a bunch of calculations, and she used used some equations that were used on the modern C4 by Yannick Baudouin and Steve Scott. And so the volume that you would need of rock, how much rock would you need to leach in order to get the cobalt that's present in the deposit? And so the volume of rock that you would have to leach, assuming that the fluids went down, leached out the cobalt, brought it up and put it into the deposit, how much would you need to have down here in order to explain the amount of cobalt that was present in the deposit? And there's an equation. The volume of rocks that you would need to leach is related to the concentration of cobalt that's present in your deposit versus the density of the host rocks that you're running through, the concentration of cobalt in the host rock itself, so the ultramafic or the bononites, etc., that you're leaching, how efficient your leaching is. For example, it can be 0, 1, 10, etc., but generally is assumed that is about 25% leaching efficiency based on, experiments elsewhere. And then precipitation efficiency is between 0 and 1. 0 be non-precipitates, 1 is 100% precipitates. And based on modern C4 systems, this is somewhere between, 3 to 10%. So if a fluid vents out of a hydrothermal vent, about 3 to 10% of it precipitates in the mound itself in those chimneys. And so she ran some calculations, and just based on various things, this is the concentration of cobalt in the bononites. This is the concentration in the peridotites here. We assumed a leaching efficiency of about 25%, and then precipitation efficiency of about 3 to 10%. And if you look at the amount of volume you need roughly about 9 kilometers if you're precipitating about 3%, close to 2.5 if you're precipitating 10% for bononites, and it's even less for the ultramafics. And so what we did at the same time was we took cross sections through this area and looked at the entire map distribution of these different units. We looked at the cross sections and assumed roughly about 600 meters thickness based on what we could see regional geology, and calculated the volume of rocks that were available. And so for ultramafic rocks, you had about 22.5 kilometers cubed in the whole area. If you look at bononites, about 10 kilometers. So either one of these things, if you leached them, there was more than enough rocks around, even with really weak leaching efficiency and really weak precipitation efficiency, to actually leach the cobalt out of the underlying rocks. There's a long way of saying that we went through a whole bunch of calculations, and the cobalt-enriched footwall rocks are where the cobalt came from, is what it says, right? So generally, the point being is that if you get cobalt-rich rocks, you're probably going to get cobalt in the deposits. Okay. And I'm going to switch gears, and the last example is just going to be one where we actually have really discrete cobalt phases. This is in what we call a luscious bite ophiolite in central Newfoundland. There's a couple of deposits in here called Wellsback and Little Deer. They have enrichments in cobalt and nickel, as well as tellurides and so on. And when we look at these deposits, they're quite similar in terms of the mineralogy, the ores, to what we see at Fire Lake, dominated by pyrrhotite, chalcopyrite. The ores themselves are deformed. We get minor amounts of sphalerite, chalcopyrite, pyrrhotite, so on. But when we look at the cobalt itself is actually in two forms, and it's associated with specific phases. So this is photomicrographs down here where you have pyrrhotite and chalcopyrite together. We have a discrete phase here called cobaltite, which is cobalt arsenic sulfide. These are occurring in with this copper and pyrrhotite mineralization. And we also get cobalt present in the pyrite, in what we call cobaltian pyrite. So in this deposit, instead of it being in pyrrhotite, it's actually present in mostly pyrite and this mineral called cobaltite. And we also get these kind of things, these little drop-like things in with the pyrrhotite associated with cobalt. These are just SEM images. There's 50 microns here. You get things like bismuth tellurides, mercury tellurides. We also get these sort of drop-like features here like this with silver telluride and bismuth telluride, and these are just maps of those different things. And these are textures that have previously been attributed in other studies to when you partially melt sulfides during metamorphism, you get sort of these drop-like features of tellurides and so on. And one of the interpretations potentially is that these things are these bismuth and tellurium and all these other things pre-existed. They existed in the pyrrhotite, and as you metamorphosed them, they came out and formed separate phases of tellurides. So some of the enrichment in these things is probably due to what we call metamorphic upgrading. And so there's lots of work to be left to do on that and so on. So this deposit, just to give you the idea of mineralogy, you get typical VMS minerals, you get these cobaltite and then all these tellurides. And the idea is that you had cobalt-rich rocks and then a subsequent overprinting by metamorphism that helped liberate some of these things. And nearby, not only do you have telluride and cobalt, you actually get some deposits that actually have pentlandite as a primary phase. And this is just an SEM image of the Tilt Cove ophiolite ores. This is actually pyrrhotite, and these are actually pentlandite grains shown in an SEM image. And so again, you have these sort of ophiolitic rocks that have lots of cobalt and nickel, and you get these cobalt nickel bearing minerals. Okay, so I'll end with this on that. This is some work from one of my postdocs, Jonathan Cloutier's work about 15 years ago or 10 years ago now. And what he argued for those deposits that I talked about earlier is that you had a pre-existing VMS deposit that had copper and so on and so forth that probably had cobalt associated with it. It undergoes deformation, and the reason that we see those discrete phases like cobaltite as well as those tellurides is that we actually remobilize these things during metamorphism and form discrete phases. So there was a pre-existing cobalt and nickel-bearing substrate. You had these rocks deposited, and then when we deform them, you remobilize these things and form secondary minerals that enriched in critical metals. So I'll leave this. Cobalt and nickel seems to be related to leaching from cobalt and nickel-rich substrates. We get deformation and metamorphism seems to remobilize these things like tellurium, selenium, arsenic, and antimony. This is important for many ophiolites and so on. And I didn't talk about this, so I'm gonna skip. And so I'll leave you with this when it comes to critical metals and VMS. I went through a whole bunch of things and everything, but ultimately it can be broke down into a couple of simple things. Zinc, you can probably leach it from footwall rocks, particularly if it's from continental crust. Continental crust generally has enrichments in zinc, particularly biotite and muscovite-rich materials. Copper is depending on the substrate. You generally can leach it. Typically, if it's mafic or ultramafic, some deposits have potential magmatic hydrothermal input. When it comes to tin and indium, it seems to be predominantly associated with magmatic hydrothermal input, often associated with copper, and to a lesser extent from shale-rich environments. These bismuth tellurides, the same thing. There seems to be a magmatic hydrothermal component, plus or minus upgrading due to metamorphism. And then cobalt and nickel seem to be enriched from cobalt and nickel-rich substrates. So things like ultramafic rocks, bononites, et cetera, and they seem to be associated with copper-rich fluids, temperatures greater than 300 degrees Celsius. And I'll leave you with this. I think that we're still early days. I mentioned this, like we already have a challenge with basic concentration data of critical metals and ores. I spent part of January in British Columbia going through archives, collecting samples from VMS deposits in BC just to get assay data of metals, because we really don't have metal data and we don't know the concentrations of these various elements. We don't know the mineralogical resonance of a lot of these things. So where are the different elements and at what concentrations of what minerals? I mentioned that there looks to be unique metal-specific substrates, but is this the case everywhere? What is the relative role of leaching versus magmatic hydrothermal fluids? Do we pre-concentrate metals? So, for example, do we have magmatism, magmatic sulfides, and then we leach them later on? What is the role of metamorphic? Is it metamorphism and structural upgrading, sulfide partial melting, and so on? And why is it that certain parts of the world are enriching these metals, and how do we find them? And I think I'm going to end with saying thanks for the opportunity. I know I covered a lot of ground, but that last slide really summarized a lot of the observations. And in a few weeks, just this whole concept of deformation, metamorphism, and remobilization on critical metals is going to be covered by Taryn Kaywood. And this has been the focus of most of her postdoc. And so she's going to really dig into it at a much deeper level than I will, and consider my arguments really the trailer to, or the trailer to her talk coming in a few weeks. Okay. So thank you.